Okay, thank you everybody for coming. So it is my pleasure to introduce Katie Skinner, who is a faculty candidate for the Autonomous Systems Search. And so Katie is currently a PhD student at the University of Michigan. She got her bachelor's degree from Princeton University. And today she's going to be talking to us about her work on unsupervised methods for perception in field robotics, including underwater environments, and I believe a bit of autonomous driving. She's held appointments at Woods Hole, and she's just recently completed an internship at NVIDIA, and I greatly look forward to hearing what she has to say, so let's all welcome her.
Hi, thank you for the introduction, and thanks a lot for having me here. It's really a pleasure to be here at CU Boulder. So I'm going to talk to you today about my work on deep learning for robot vision in natural environments. And when we talk about robots in natural environments, we usually refer to this as field robotics. So field robotics refers to robots deployed in natural, unstructured, dynamic environments where we might have very varying environmental or weather conditions, varying lighting, and this leads to very unique challenges to robotic systems. So field robotics encompasses a range of applications in different environments, including autonomous underwater vehicles to be deployed in deep sea applications, to unmanned ground vehicles that might be observing agricultural environments for precision farming. And I think the hot topic in recent years is putting self-driving cars on the road. So all of these applications are encompassed by the term field robotics. And today I'm going to mostly focus on the topic of my dissertation work, which is in underwater robotics, but I'm going to save a little bit of time at the end to talk about how it relates to problems that we see on land for self-driving cars as well. So when we're working on underwater robots, we really have to be willing to get our feet wet. And this is from a field deployment that I did in Alpena, Michigan, so out in Lake Huron, where we were collaborating with USGS to go and observe these invasive round goby fish species. So USGS was really interested in being able to send out robots to automatically detect these fish and to count them and to be able to monitor their populations over time. So we took our Iver autonomous underwater vehicle, attached with cameras, deployed it in the lake, and unfortunately, we couldn't find the fish anywhere. So we ended up just gathering a lot of imagery of the Lake Huron seabed. And that's maybe just one of the challenges of field robotics, is that you never really know what data you're gonna get in these natural environments. We can't tell the fish that we would like to take pictures of them. But it did give us this cool GoPro footage. So the goal of this work was really environmental monitoring with autonomous underwater vehicles. And if we take a step back, really for centuries, humans have been trying to map and explore and understand underwater environments. And these environments take up 70% of the Earth, and it's really incredible how little we know about them. So we have actually better understanding, higher resolution maps of the surface of Mars than we do of the seafloor, which is really incredible if you think about it. It's right here. But we've been trying to understand these environments since the early 1800s, were the first, known efforts to map the seafloor. And these were very manual processes. So this is actually a lead line, literally lead attached to a rope. And people would go out in boats and drop these lead lines into the water, see where they hit, and measure the length of the rope. And I mean, if you wanted to map 70% of the Earth this way, I think it would take quite a long time. So luckily, we've advanced over the course of time and moved on to more efficient methods for mapping and exploring these environments. So this was actually from wire dragging in the early 1900s, where now we are able to use teams of boats that carry a wire with weights at different heights, and they basically drag the wire along the seafloor and see what it hits. And if you have it submerged to a certain depth and it hits something, you know, okay, we have something shallower than this depth. So this again sounds like a very painful process. Like it might take a really long time, but we did get to see some sparse maps of bathymetry this way. And if you flash forward to now, it's pretty incredible the advancements that we have to map the seafloor. So the state of the art for high resolution structure is using multi-beam sonar from ship-based inspection. And with this method, we can start to think about gathering really large-scale 3D maps of the environment. But as I mentioned, we still have a very low resolution map of the entire seafloor, and the current resolution of about 95% of that seafloor is still to 1.5 kilometers. So we still have a ways to go structurally. And here I'd like to also point out that structure might not be the only thing that we care about, right? So it's really important for a lot of applications, but there are other applications where we might want to be able to observe different things about the environment. So I've done a lot of collaboration with marine biologists who are interested in gathering really high resolution images, color images of the seafloor. And you can see how this might be important because on the left we have a healthy coral, and when the coral is healthy, it's actually in a symbiotic relationship with algae that lives on the coral. And when the coral becomes stressed, this algae gets expelled, leaving the base of the coral, and this is what we call bleaching. And you can tell some structural changes between these two examples of healthy and bleached coral, but what stands out to us the most is really the color. So a lot of my work has focused on how we can gather high resolution color information of subsea environments. And to do this, we have to use cameras, right? So cameras are the best way for us to gather this color information. So I've worked a lot with stereo cameras, where we actually have two cameras that are highly constrained geometrically, and this, like our eyes, actually allows us to have some depth perception of the scene. So with stereo cameras, we can actually gather color and structural information of the scene. But unfortunately, we have to be able to send these cameras down to the bottom of the sea. And in the last few decades, I think something that's really advanced is the availability of commercially viable options for carrying out marine robotics research. So we have really a range of platforms depending on the application that you're interested in, where you can modify these platforms to attach whatever sensors you want, and they do pretty well from 100 meters to the Remus 6000 that goes 6,000 meters, but there are other vehicles that can go to the deepest part of the ocean. So we have now really a lot of commercially available platforms that we can use to put our cameras on board and send them out to map the environment. And from one underwater survey, we can gather actually terabytes of image data. So this is just a massive amount of data. And now I think the question really is, what do we do with this data? And what processes can we automate to move technology forward? So one project one application that I've worked on is developing these high-resolution 3D models of coral reef structures. So this is actually about a 20 meter by 10 meter section of a coral reef in Bermuda. And from this, scientists are able to measure the biomass of the coral, but also they want to be able to tell exactly where their scientific instruments are within that coral habitat. So from providing this 3D model, or enabling us to collect and compute this 3D model, we can actually learn a lot about these environments in this way. And I think there's a lot of other questions that we can ask too, right? So how do we process this data? What kind of information can we extract from it, from the raw images, to go from thousands of images to a 3D model like this? And then once we have higher level information, what can we learn from that higher level information? And can any of this be automated in any way? So these questions kind of span the field of robot vision. Is how do we put visual sensors on robots and use them to observe environments and perform low-level, mid-level, and high-level tasks. So if we think about low-level vision in terms of how human perception might work, perhaps we gather an image and it's noisy or it's distorted in some way. And we can think of image restoration as a low-level vision processing or image processing task. So we can undistort this image to go from a raw underwater image to a restored accurate color description of our scene. And I'm going to talk a little bit about work I've done in this domain. And if we want to move across the hierarchy, mid-level vision tasks really incorporate how we can represent this information or these raw images in different ways. What other kinds of information can we gather from them? So for example, dense depth estimation from stereo cameras, or 3D reconstruction computed from imagery. And this takes us all the way to high-level applications, such as segmentation and object detection. So I'm not going to focus on this work too much, but for example, how do we segment man-made structure from natural environments? And what other things might we want to observe, such as fish detection or automatic biomass measurement in these environments? So I'm going to talk to you a little bit today about applications across the span of robot vision. And many people have come up with solutions to think about these problems, and I think they can be sorted into kind of two main approaches, which are model-based approaches and data-driven approaches. And if we think about model-based solutions and what those are, for example, if you want to track a trajectory of a ball, one way you could go about doing it is learning from the physics, right? Gathering or coming up with a model of what's happening and using that to take a very complex process and put it into an interpretable model where you have fewer set of parameters that you need to know in order to maybe predict where this ball is going to fall, right? So we have very explicit rules from physics about how this system might work, and to us it's very interpretable, right? Once you start to learn the laws of physics, this might make sense to you, and these are very structured solutions, which we as humans like this structure, interpretability. And it kind of limits the complexity, right? Now, instead of having to know every single thing that goes into this process, you can actually boil it down to a smaller set of parameters. But unfortunately, we can't possibly model every thing in the environment, and this is one challenge to using model-based approaches in field robotics, is that we have varying environmental conditions, and we can't possibly model all of these conditions. And on the other hand, we have data-driven solutions. So in data-driven approaches, maybe you would collect a lot of examples of the ball being thrown and see where it starts and where it ends, and see if you can learn something from the data. So you can learn a lot about very complex systems directly from data, but you need a lot of training data in order to do this. So kind of a main point of my work in data-driven approaches is using deep learning. And deep learning, for supervised learning, you might gather a lot of training data, which goes into the input of your model. And there are a lot of hidden layers, which gives it the name deep learning. And then you have a labeled output or ground truth label in your output layer. And you're actually learning what the parameters of these hidden layers are. But to some extent, the hidden layers are a black box, and you don't actually know why they're learning what they're learning. You just know that you have your input data, and it's learning to go from the input to the output. So one issue we have in field robotics is, where do we get this ground truth, right? So underwater, if we're thinking about ground truth structure, color, some things may never have even been seen above water, so we don't actually know what the color, what their true color is. So how are we going to gather ground truth for problems like this? So for a lot of I think for a lot of tasks in robotics, it's difficult to gather clean data, and it's difficult to gather ground truth for the specific thing that we might want to achieve. So moving towards unsupervised learning is a really exciting field for me. So as I mentioned, I'm going to talk about these different solutions across several robot vision tasks. And first, I'm going to go into work I've done in underwater image restoration. So when most people picture underwater images, they picture something like this, where you have very brightly colored coral, brightly colored fish. And this is mostly thanks to Photoshop, unfortunately for us. What we actually get looks more like this. So even 6 meters off the ground, you can't really tell where you are. 4 meters, you start to make out maybe some cloudy features. And as you get closer to 2 meters or 1 meter, that's kind of the sweet spot for our imaging surveys. So we need to send our robots to be about 1 to 2 meters off the seafloor if we even want to make out features in these scenes. Right, so that's very challenging, and I think it's important if we want to be able to use a lot of visual tasks developed on land to be able to restore these images appropriately. And in order to do that, I think it's really important to think about how these images are formed, right? Why do they look like this? And we can look to physics to tell us a little bit about the process of underwater image formation. So as light travels between the camera and the scene, it interacts with particulate matter in the water column, and it can be scattered or absorbed. So absorption leads to attenuation, and this attenuation is wavelength dependent and it's range dependent, and that's what's leading to this blue-green color in the scene. So the red light has been almost entirely attenuated, and this is an exponential process as you get further away from the camera. And we also have backscattering, which is very similar to fog in air, and that's leading to this haze effect across the scene, especially if you have sideways-looking cameras. It's much more noticeable.
Is it normally uniform always, or it does vary by depending on the...
It varies. So, which moves to the next slide. So if we want to look at the physics-based model, we can see it's an exponential function, and it's dependent on this attenuation coefficient, and that is a very complex coefficient that depends a lot on the properties of the water, maybe what is dissolved in the water, and that can change to be, that can change to cause your images to look blue or green or even brown in river water, right? So it really depends on the environment. And if we look at the initial colors, for example, of a color board, and an example of what that might look like underwater, we can see really how we lose a lot of the red colors for ocean environments. But this also depends on a lot of other factors. So the final radiance of the scene is an addition between the direct transmission, which has some information about the scene. So this is the initial radiance of the object that you're looking at. So it carries some information about the color of the scene, although it's been attenuated. And then we have the backscattered light that actually is from light that gets scattered back to the camera before it even hits the scene or hits the object of interest. So it's a very complex nonlinear process, and it depends on a lot of factors like your viewing angle, your distance to the scene, the initial spectral color of the object, and other effects as well. And this leads to some important challenges in computer vision. So on land, if you look at one object from a viewing point and then you move to a slightly different viewing point that's at a different distance or a different angle from the object, you kind of assume some measure of photometric consistency or brightness constancy, which of course breaks down on land in some situations, such as specularities. But underwater, it always breaks down due to these range-dependent effects. So if you move to a different location, that object can actually look much different. So your resulting image will look much different than your previous image. So this leads to assumptions that we use on land for computer vision, breaking down due to these range-dependent effects. So the goal of my work is to be able to improve perception for underwater robotic systems. And one thing that I've focused a lot on is how we can actually take this raw data and put it into a usable form to do higher level vision tasks. So looking at how we can perform underwater image restoration to give us accurate color, but also to restore this measure of photometric consistency as if the images were taken on land. And since we don't have ground truth of this color of underwater scenes, I've looked to developing unsupervised learning methods to do this. So unsupervised learning means that I don't have labels as I would in supervised learning, and I want to perform color correction and dense depth estimation of underwater images. So in order to relax the need for labels, I've turned to other sources of information that we have about these environments. So we have a strong knowledge of the physics based process of underwater image formation. How can we incorporate this into a learning-based framework in order to form an unsupervised learning approach? And then I've also looked to geometric constraints as well as knowledge from image processing about natural image statistics. So first I'm going to tell you about a project that focuses on incorporating physics-based models into unsupervised learning frameworks. And this was work called WaterGAN, where we formed an unsupervised generative network to perform real-time color correction of monocular underwater images. So instead of stereo, we have one camera, so we have one static monocular image of the scene. And this is a two-stage process. So the first stage, called WaterGAN, is actually allowing us to form a training set of underwater images paired with ground truth, color, and depth. So WaterGAN takes an input RGBD, so color and depth data set from just any in-air online data set, and it puts it through to generate a paired synthetic underwater image that actually mimics the distribution of underwater images that you've gathered and you would like to restore. And once we have this paired imagery, we can use a supervised underwater image restoration network to go from the synthetic underwater image to the ground truth, color, and depth information. And then during test time, we can test on real underwater images, and we actually see that we have accurate and consistent color corrections, even though we've only trained on this synthetic data. So to go a little further into detail of how this works, WaterGAN is based on generative adversarial networks. So GANs have become popular in recent years, and they're based on two networks, a generator network and a discriminator network. And the generator network is getting some input, traditionally noise, and it's trying to project that and generate fake data from that input. The discriminator network now gets this fake data and it gets the real data that you're trying to match, and it's trying to determine whether the image that it's getting is real or fake, right? So this is really great because now we have our labels for free. We know which images come from the generator network, and we know which images we're inputting as the real data. So this is what allows it to be unsupervised. And then the bonus is that the generator network actually sees how the discriminator does. So the generator network can learn to improve its generative process to generate more realistic fake data to fool the discriminator. So in this way, your synthetic data gets better and better as the networks train and kind of compete. So WaterGAN has a generator network and it has a discriminator network. And the generator network takes in a noise vector, but also a true color and depth from just an in-air data set that you can download from open source Connect data. And it uses the process of underwater image formation to learn the different stages, so attenuation and backscattering, also vignetting from the camera, to output a synthetic underwater image that looks like a real image that we want to be able to correct. And to give you an example of how each stage might work, it's a hybrid method. So the attenuation model is based on the physics-based model of attenuation underwater. So we're actually learning the attenuation parameters for this data set to output just an attenuated image. And the backscattering stage is more of a shallow learned network. So we're actually learning this mask that gets added to the attenuated image. And in this way, it's kind of a balance between using the physics-based model, but also leaving us some room to learn other effects as well. And the discriminator is learning based on the output synthetic image and the underwater image. So after we train WaterGAN, we now have a paired data set where we have synthetic underwater, depth, and true color in air. But we want to do underwater image restoration, so now we want to learn to go the other way. So this underwater image restoration network is a supervised network, and it takes an underwater RGB image, and the first stage learns the depth map, and then that gets concatenated to the underwater image and is put through a second stage that learns to correct this image. And of course, we have to validate our approach, and to do this, we actually build very large fake rock platforms, and we attach color boards to the platforms. So this might be 2 meters by 1 meter wide, and the rocks are about 1 meter high, and we can submerge these fake rocks in water. So in this case, a pure water test tank that we have on campus, and we take our stereo images. We only used one camera for the training, but we can take our underwater camera and survey these fake rocks in the pool. And after we train these networks, we can test on this real data. So we have the real underwater image that's input into our trained model and our output restored image. So what we're looking for is color accuracy and also color consistency. So to look to measure color accuracy quantitatively, we can look at the color board imaged in air, and we look at each color on the color board. So there are 6 colors, and we take the Euclidean distance of the intensity normalized color. So we normalize for the intensity, and we use RGB space for our error metric here. And we compare to a range of methods. So the raw underwater image is the initial underwater image compared to in-air color. And histogram equalization and gray world are image processing techniques. So these methods give very visually appealing results. They act to stretch the contrast or shift the image histogram to match what we expect for natural images. But they have no knowledge of this range-dependent effect. So they don't know how the physics of underwater image formation works. They're just looking at purely the image histogram, for example, to stretch the contrast of these images. The modified Jaff-McLamry model is a physics-based approach, but here we used coefficients that have been calibrated for pure water test tanks. And as you can see, if you don't calibrate it exactly for your specific tank, there is still a lot of error here, even if we assume coefficients for pure water. And lastly, we compared to a paper by Shin et al., and that was the only deep learning paper available at the time for underwater image restoration. But I should say that they focused mostly on correcting backscattering, so image dehazing. They weren't necessarily focused on color correction as we were. And you can see we have a good improvement across, especially the red and the blue channels. The green, I think we suffered a little bit because we might have had some overcorrection here as the initial dominant color in our images was green for this data set. But we do pretty well compared to these other methods. And of course, histogram equalization gives a very nice result. But when we look at color consistency, I think that's where our method really shines. So I think this is easiest seen qualitatively, but as you can see, for these methods that don't have knowledge of the range-dependent effects, if they're going to correct these images that are taken at different ranges, they might correct them to be different colors completely. So this rock that's the same down here that's supposed to be gray is actually purple in another image that's corrected. So our method scores much higher on the consistency test in that when we view the same feature from different viewpoints, we want to see that it has consistent color in the correction. So the contribution of this work at the time was really state-of-the-art underwater image restoration, and it was one of the first deep learning approaches, or the first deep learning approach for color correction underwater. And since then, it's spurred kind of an interest in underwater image restoration, which is fun. But it was an unsupervised learning approach that was really enabled by incorporating physics-based knowledge of underwater image formation to enable us to make this an unsupervised learning process that both restores images accurately but also consistently. And we made this data set and the code open source for the community. So that was an example of a low-level vision task. And I'm going to talk a little bit about a mid-level vision task that I've done more recently for both color correction and dense depth estimation of underwater images. So this work focused on stereo vision. So now that we have stereo cameras, we can still look to the physics-based models to give us some information about the problem. But we also have these very constrained, these cameras that are very constrained geometrically with respect to one another, and we can leverage this information as well. And lastly, we look to image processing. So we have some loss that looks at the gray world statistics of the image, the final image, to inform our learning approach as well. And this is recent work that will be in the upcoming ICRA. But the main pipeline takes in raw stereo images. We have a disparity estimation module that estimates the disparity from the left and the right images. And then this disparity gets input into the color correction module with the raw underwater image as well. And as a result, we have both estimated disparity, which is related to the depth map of the scene, and we have a corrected underwater image. So to just talk through the first part at a high level, we've really used the geometric constraints for stereo images to form this network. So it's a self-supervised network, and it's based on the idea that if you have two images, a left and a right image, and you are able to estimate the depth of the scene, you can actually warp the left image to the right image using this information about the depth, because that tells you something about the geometry of the system. So this is used as a loss to make this an unsupervised learning, a self-supervised learning approach for disparity estimation. And now that we have an initial estimate of the disparity, we can use this for training our color correction module as well. And to do this, we look to the physics-based model, so we know that the corrected image will depend on both the range and the initial color. So these are our inputs to our network. And we use some knowledge knowledge from image processing to tell us about the desired statistics of the output images. But it still takes input depth information to keep this grounded in the physics. And we can see some qualitative results here. Hopefully you can see the disparity map. But the input, so if this is one input raw image, we can estimate the disparity, which is related to the depth of the scene. And we have a very dense disparity estimate. And then we have an output corrected color. So currently this runs at about 2 frames per second on my nice Titan X GPU on my desktop. But of course, we're roboticists, so we want to work towards deploying this on a robot in the field. So working right now to make this network more lightweight so that we can perhaps put it onto as a first step, onto a laptop where we're connected to a tethered robot in an underwater environment, and we can stream the underwater images where we have a laptop with a nice GPU giving us output corrected color and disparity. And this would give us kind of an online estimate of how our robot survey is going. So the contribution of this work was really, that it was a novel network for dense depth estimation and color correction from underwater stereo images. So this was, I think, the first work for underwater stereo color correction from a learning-based approach. And again, it's this hybrid, model-based, data-driven framework. And we're able to achieve consistent and accurate results without using ground truth labels. So now that we have this dense depth and color information, one application that you might think of using this for would be to put this into a method for terrestrial real-time dense depth map or dense 3D reconstruction. So after we achieve our goal of speeding up this pipeline, we would like to be able to put this directly into, for example, a fusion-based approach that performs dense real-time 3D reconstruction from this consistent color correction across a longer survey. So that touches a little bit on low-level and mid-level vision applications. And I'm going to skip over some of our 3D reconstruction work, but if you're interested in reading more about that, you can see our Oceans or ICRA papers. And as I mentioned, I'm not going to talk about scene segmentation for the underwater application, but instead I'd like to talk about high-level visual tasks that have been developed on land. And so this is work that I've done recently in collaboration with the Ford Center for Autonomous Vehicles at University of Michigan to work on object detection and also dense depth estimation for terrestrial applications. And autonomous driving is kind of a buzzword right now, and people are really excited about it because of the potential that it has to offer benefits to society. So the one benefit is if we can develop these autonomous systems that can drive on our roads without human input, we will have increased safety, right? It'll be less prone to human error. We'll have improved traffic flow because we can really optimize these vehicles to be more efficient on our roadways. We'll have increased mobility for for humans, or for people especially who aren't able to drive currently, perhaps due to a disability, now they'll be able to use these vehicles for transportation. Decreased costs, because again, we have improved traffic flow and greater efficiency of these vehicles, which leads again to reduced emissions, and the list goes on and on. So people are really excited about autonomous car or self-driving cars and how autonomous driving can move society forward and bring all of these benefits to us. So I worked a little bit across two specific applications for autonomous driving, and I'm not going to talk too much about the dense depth estimation paper, but it is somewhat related to our method for underwater depth estimation from stereo images. But I'm going to go into some more detail of work for object detection in urban driving scenes. So I'm going to focus on work that was presented at an ECCV workshop for object detection in urban driving scenes. And deep learning has really been able to boost our capabilities of visual tasks for, especially for autonomous driving, where we have a lot of open source data that we can leverage to benchmark and compare our methods. And this has really pushed this field forward. But deep learning has been really revolutionizing the field of computer vision in this domain. And there's still a lot of things that we can't handle, right? So especially when we're thinking about challenges specific to field robotics, there are things that our learned systems still really struggle with. So for example, varying weather conditions. If you aren't able to gather enough data of, for example, fog in the road or cars in rainy environments, this is really a problem for supervised learning methods that might mostly have training data from sunny days, clear skies, and then a much smaller sample of training data from these foggy environments. We have variable lighting, so even when we do have sunny days, that might not be to our advantage because this leads to varying shadowing effects across the scene, which is hard to predict or anticipate, and it really depends on what's in the environment or maybe even the season or the time of day. And all of this can really affect our sensors. So if we're using cameras as our main sensor, we have a lot of challenges deploying these sensors where we might see oversaturation in our images due to overexposure in certain sunny areas. And that's where you see these white effects where the information is actually lost in this part of the image due to overexposure. So an alternative to gathering as much training data as possible in as many different environments as possible is to start to look towards other methods of gathering training data. So we've been really interested in training from simulation for visual tasks. And there's a lot of interest in this area, so there are a lot of open source data sets, especially in the domain of autonomous driving. And we can look at real data sets, so maybe you've heard of Kitty or Cityscapes, and these are open source data sets that have ground truth bounding boxes for cars or ground truth segmentations of the scene so that you can train these networks and compare them. And if you look at the simulated images, we have Virtual Kitty, which is actually developed to directly match the spatial distribution of the Kitty environment. And we also have other simulation engines like GTA, our lovely video game rendering engines. We can actually extract images from GTA with dense labels of the scene. So it seems like simulation might offer a really nice way for us to gather training data of different spatial configurations, different environmental conditions really quickly, right? Compared to putting a car out in the natural environment and driving around as much as possible through as many seasonal conditions as you can, we could maybe just learn to render those conditions here. And we would get our labels for free, especially for tasks that might be really challenging to densely label ourselves, right? So a lot of work has gone into labeling ground truth, for example, for dense segmentation of the scene. So that's pixel-wise segmentation of what every pixel is in the image. And this actually costs a lot of money to hire someone to label your data. So looking at simulation as a cheaper alternative as well. But unfortunately, right now, the state of the art shows that it's actually much harder to train on simulated data and generalize to real data. So our accuracy actually drops off quite a bit. And one thing we hypothesized of why this might be is because of the effects of our actual sensors in the real world, right? So you can look at all of these different data sets, and even to your eye or my eye, you can tell which one is real and which one is fake. And if we can tell this so easily, maybe this is what's affecting our networks. And one of the reasons, or one example you can see here is if we have oversaturation due to overexposure in our images, or if we have different shadowing effects, or even just different tones of the color space. And what's interesting to us is that even in real images that were taken, these data sets were both taken in different towns in Germany from cameras mounted on a car. Even these real data sets look pretty different to us, right? If I gave you images from these data sets, you could probably pick them all out individually. But we were focused on transferring our learning from simulated images to real images so that we could leverage the benefits of using simulated data in learning frameworks. And what we came up with was a pipeline to augment our original synthetic or our original simulated image to look more realistic according to specific sensor effects that we picked out. So here we're modeling 5 different sensor effects, including chromatic aberration, which has been shown to really degrade the performance of learned networks. We're also modeling the changing color tone of the image, as well as the exposure function. And other effects such as noise and blur. So we have an augmentation pipeline now that uses physically realistic effects in augmentation for these images. So you might compare this to traditional approaches to augment images for network training, which might be like rotating an image or mirroring an image. But these effects are based in a physically realistic reason for why we think these images look distinct from real images. And in our results, we can see that we do get some benefit from augmenting images in these ways. So if you look at the green detections, these are correct if we train just on simulated data. And then the extra red boxes were actually missed in the original, if you train on just simulated images, but detected when you trained on our augmented images. And it's easier to see this if we look at specific failure cases that we were seeking to improve upon. So in this column, we see images that were only trained on the base simulated images. And the blue detections are what that network caught. But you can see that there are some clear misdetections, especially this white car in this very bright space. And this was a specific case that we were actually trying to improve upon using our augmentations for exposure. And in the bottom image, you can see some of the cars that have slightly different lighting pattern or are shaded maybe in an unexpected way. So these were really the cases we were trying to improve. And now you can see in the red box, these are our improvements over the initial baseline method. So the red boxes show cars that we were able to detect using our augmented images in training.
Quick question.
Mm-hmm.
Do you do any tracking here? Or is it
No, they're all single frame images. So even, so this video was single frames detected, yeah. But this has led to a novel augmentation approach for training on simulation and testing on real data. So it's what we call sim to real. And to do this, we've incorporated knowledge of the actual sensor effects in the learning pipeline. So we saw that when we compared this to traditional spatial augmentations, we actually outperformed traditional augmentations for simulated images. And what was interesting to us as well is when we compared our results when trained on a small set of maybe 2,000 images, we actually outperformed training on about 20,000 simulated images. So to us, that hints that maybe the variation in these physically based effects and these sensor effects is just as important, or at least very important to the learning process to make these methods more robust. And we saw that this improved results for the typical failure modes that we set out to improve upon. And we've extended this work. So the first augmentation pipeline for the workshop was actually just randomly sampling over parameters of these functions that we chose to mimic or to model specific sensor effects. And since this paper, we've extended this to actually learn the parameters of these sensor-based effects for modeling specific data sets. So for example, if we want to go from virtual kitty to kitty, we can now learn what the parameters that would transfer the virtual images to specifically the kitty data set might be, instead of randomly sampling these. And this has improved upon the random sampling. So I want to talk a little bit about future directions, and I'm really interested in developing advanced learning and perception to enable robust, real-time autonomous systems. And I'm really interested in applications across field robotics. So as I've mentioned here, I've worked a lot from underwater to in-air applications. And what's really exciting to me about all these applications are the parallels and the challenges between them. So in each of these cases, we've had very variable environmental conditions that have impacted our ability to form robust learning-based approaches. And I've looked to developing hybrid model-based data-driven solutions to address these challenges and moving towards methods that do not rely on manual hand-labeled data for this learning process. Right, so in the end, we want our systems to be adaptable to unseen environments. So this really touches on the problem of generalizability and how can we develop systems that, especially learning-based systems that we maybe trained on one data set and we want to put into a different domain. So for example, even training on simulation and testing on real data is a problem of generalizability here. And we also want to work towards transparent learning-based systems. So we saw that typically these deep neural networks are black boxes. We don't actually know what they're learning or why they're learning it. And I think one direction to go in towards deploying autonomous systems in the real world is really to increase the interpretability and transparency of these systems so that we have trust and enhanced safety as a result in deploying these systems in the real world. And finally, I want to be able to leverage different sensing modalities to perform intelligent tasks that advance society. So maybe tasks that we haven't even thought of yet, pushing in directions that will push the bounds of what we're currently able to do with robotic platforms. And to think about how these problems in more depth, I like to think about how robot learning occurs right now, right? And I've mentioned a lot of this throughout my talk, but currently you might put a robot in the natural world, attach a sensor, for example, to detect apples in a tree. You would gather a lot of images of these apples and manually label the bounding boxes for what you want to pull out of these images. You could put this into a supervised learning framework where you have input images of all the apples that you've collected and the output labels in blue of where the apples are in those images. And you would train this network to hopefully be able to take in new images of apples and tell you where that apple is. But then if you go into a different environment, or even if one thing changes, for example, the weather, right? The weather changes all the time, and if you haven't gathered data in this specific environment, then your new network or your trained network might just need to be thrown away, right? So you might see a big performance decrease when you're training on these images gathered in a rainy or a foggy environment. And this really speaks to the need for increasing generalizability in our learning-based systems for autonomous systems. And again, I'm really interested in looking to alternatives to hand-labeled data, and I've talked about a few of those here. So I've talked about training on simulated data, I think is a really exciting future direction, and one that has definitely a lot of room to improve right now. But I think if we could figure out how to make these learning systems generalizable from simulated data to real-world data, this would really change our approach and our philosophy of robot learning. I'm also really interested in unsupervised and self-supervised learning, as I've talked about some examples today. And I think looking to interesting alternatives for labels, such as using a different sensor to do automatic labeling for the sensor modality you're interested in. I think there are a lot of interesting questions of how we can form unsupervised learning approaches, especially in robotics, where we have a robot in the real world, and we have such a rich understanding of a lot of phenomena that happen in the real world, right? So we have knowledge from physics. We have very well-formed solutions that we've used for decades, and how can we incorporate or leverage all of this knowledge and these solutions in learning-based frameworks? And I think there's a lot of industry interest, especially in training from simulated data. So recently, papers put out by Google and NVIDIA for both perception-based learning as well as reinforcement learning from training from simulation. So looking to these companies to provide collaboration or academic or support for these projects. Another direction I'm interested in, as I mentioned, was transparency for learned systems. So this is a really big push for explainable AI, and this is a big interest to DARPA, and you have also professors working on this here at CU Boulder, and it's a really exciting field that I think has a lot of room for input and new solutions, right? So the current systems that we use are black box systems. We don't know why they decided why they chose the solution that they chose. We just know the input and the output that we gave for training. So you might want to ask, when do you succeed? When do you fail? How confident are you in this decision, right? Incorporating some level of confidence or uncertainty into the actual solution that you get. So working towards explainable AI or transparent learning approaches where you would actually be able to gather some understanding of why the network chose these solutions. I think there's a lot of interesting directions for how you can do this. And one of them, as I've talked about here, is incorporating knowledge of the physics or incorporating models that we have currently that are very interpretable to us. How can we kind of balance the learning and the model in our solution, right? So how can we find that balance where we still have an interpretable system, but where we don't sacrifice any accuracy in what the learning-based system is giving us? So I think that's a really interesting direction for future work. And lastly, something I didn't get to talk about too much, but that I've worked on a bit in my PhD work is actually computational imaging. So something that's really exciting to me is now the availability of a wide range of sensors that have advanced sensory capabilities, right? So a lot of these sensors are not yet commercially or not widely commercially available, or maybe they're starting to be more widely available. And a lot of that is driven by this advancement in computation and what we're able to do on remote systems, right? So, for example, light field cameras actually have a microlens array between the image, between the lens and the imaging plane, and this allows it to capture slightly different perspectives in one shot. And when you gather these constrained perspectives, you can actually pull out depth information about the scene, but you can also, for example, make some conclusions about obstructions of your objects that you're looking at, right? But these sensors currently, they provide a lot of information, and that's a lot of data to process. And I think there's a lot of open questions of how you can most accurately or how you can most interestingly process this data for a different task, especially in robotics. And omnidirectional cameras are becoming more and more popular, but again, these images don't look like traditional images from the cameras we're used to working with, and they gather much more information about the scene in a single shot. So how can we use this massive amount of data that we're able to gather? That's very rich sensory information, and if this can enable us to do new tasks that we maybe haven't thought of yet. And in terms of applications, as I mentioned, I'm really interested in field robotics, so continuing my work in underwater robotics. And this follows the research thrusts of several funding organizations. So the Office of Naval Research, as well as NOAA, I've collaborated with for several projects. I'm also interested in precision agriculture, or putting unmanned ground vehicles out into the wild, where you might have very variable lighting and weather effects. And NSF has the National Robotics Initiative that's also teamed with USDA to explore this application space. And lastly, continuing my work for autonomous driving, I think is a really exciting field right now, especially from all of the interest from different groups, right? From government to industry to academia. I think that everyone's really excited about self-driving cars, but there are still so many open problems that we have to solve before we have safe, trustworthy, robust systems on the road. And I've worked with the Ford Lab at University of Michigan, but a lot of other big industry players in this field are interested in this problem right now. So thank you for listening.
Do we have some time for questions?
How complicated is it to make a model that makes the weather effect?
Yeah, actually, my collaborator on the sensor effects project is looking to modeling weather effects right now. So I'm not really sure how far she's come, but something that I think is a really interesting way to frame how we think about these problems is that what's really challenging is that these effects cause some information loss of our image, right? And whether it's rain across the camera or fog or overexposure, we're just losing some information about that object that we're trying to observe. And I think framing it in the way of how can we make learning systems that are just robust to this loss of information is one way that I think about it.
You have to compare with the kind of ground truth somehow?
So yeah, for the work on simulated data, we compare to just the baseline of training on simulation. But yeah, I think probably for weather effects, I can't say there are really real data sets that have both in air and the exact same scene with weather. So it is kind of hard to validate that outside of simulation. Yeah.
So specifically, my question is with respect to the paper on water design. So you were basically using a particular model to modify the data, or you said that your final performance of the model had lesser performance on the green channel, and you felt that that sort of statistic was because your model was flawed, or your model had the data that you were inputting was more of a green color. So,
Yeah.
So my question is essentially, when you build systems in which you have incorporated your physical model, how do you then quantify the performance of the model with respect to errors within the performance of the data-driven model with respect to errors within the theoretical model that you use?
Yeah, so one of the methods we compared to was that modified Jaffe-McLamory model. So that is the physics-based model for attenuation. So I guess comparing the error the error of our learned model to that, perhaps. But even there, we used the pure water attenuation coefficients that have been found experimentally elsewhere. So I think maybe a better way to do that would be to actually calibrate for our specific test tank, and then you could see precisely the difference between the extra learning component, the learned component. Does that answer your question?
No, I think I've talked to you all.
The physics model that you develop to create synthetic images, normally these models have a lot of parameters in them. So generating that data, and network seems to be learning the inverse of that function. So the combination of values of all those parameters could be very large. How do you know that you are capturing really what physically is happening for those parameters?
Yeah, that's a good question, and I don't know that I have a good answer to it, but my intuition is that the model that we use, or we learn a model for the attenuation stage, and then for the backscattering stage, it's a learned approach. And I have a feeling that whatever isn't captured by the attenuation model is being picked up. Maybe even image noise, right, could end up being modeled by that backscattering phase. So it's maybe unfair to say that it's exactly parallel to the stages of underwater image formation, but inspired by it.
Time for one more.
Our lab is working on subterranean visual navigation right now, and so we're looking at what do you do when your light source is on board. Is that something you've dealt with in underwater environments also? Or?
Yeah, so I've mostly worked in shallow water environments and making assumptions about the ambient light, but definitely working with artificial light sources is a different problem, but something that we see in deep sea applications. The effects that your specific light source has on the image, and also which part of the image it illuminates, or shadows that are caused.
Okay, so let's thank Katie again.